In the last video, we have tried to study about the thermodynamic principle of metallurgy. We have seen the first conclusion that delta G must be negative. In the second conclusion, we have seen that if we couple two reactions and if overall delta G is negative, we can say that the overall reaction is also spontaneous. So, what does it mean? Let us try to understand it in detail. So, the process of interpretation involves coupling of the two reaction, getting the sum of their delta G and looking for its magnitude and sign. Such coupling is easily understood through Gibbs energy change delta G versus T or temperature plot for the formation of oxides. So what does they try to tell us is that when we couple any reaction and we see if delta G is negative, this coupling of these two reaction is going to be spontaneous. To understand this process or to understand the process of coupling of reaction easily, we'll have to draw a plot of Gibbs free energy versus temperature, and by doing it so we can understand the same thing better. Now we are going to study about the Ellingham diagram. So let us see what is the definition or what is Ellingham diagram. The graphical representation of Gibbs energy was first used by H.J.T. Ellingham. This provides a sound basis for considering the choice of reducing agent in the reduction of oxides. This is known as Ellingham diagram. So what we can say that Ellingham diagram is a plot of delta G versus T. This delta G per mole of O2 for the formation of oxide of a metal. This is how we can understand. So here, or for the oxide of any element. So here in the Ellingham diagram, we study the plot of delta G per mole of O2 for the production of element oxide, and on the x-axis we plot temperature. So how does the formation of oxide takes place if we keep on increasing the temperature, and what are the changes into the delta G values? Such diagram help us in predicting the feasibility of thermal reduction of an ore. This diagram, which is known as the Ellingham diagram, actually help us to know which reaction is possible for the reduction of the metal oxide. Criteria of the feasibility is that at given temperature Gibbs energy must be negative. That was our first conclusion, that if delta G is negative then the reaction is going to be spontaneous. Here you can see this is the diagram. This diagram is simply known as the Ellingham diagram. You can see it very easily. On the y-axis we take delta G, that is kilojoule per mole of oxygen. So this is the delta G for 1 mole of oxygen when it is used to produce the metal oxide. On the x-axis we take temperature. You can see the value of delta G starts from 0. So we have taken all the delta G value which are negative, and we have taken the temperatures ranging from 0 degree centigrade to the 2000 degree centigrade. So we have taken the huge range of temperature even. You can see the various graphs which are available here. This is the graph for the formation of the magnesium oxide. You can see it easily. This is the graph for the formation of the aluminum oxide. This is the graph for the formation of the zinc oxide. This is the graph for the formation of the carbon dioxide. This is graph for the formation of the iron oxide. This is the graph for the formation of the cuprous oxide. This is the graph for the formation of the carbon dioxide. This is the graph for the formation of the carbon monoxide. There are two type of graph. The graph which are sloping down, these graph are known as the positive slope graph, and this graph which are going upward, they are known as the negative, sorry, this graph which is going down, they are known as the negative slope graph, and this graph which are moving upward, they are known as the positive slope graph. So we have two type of graph, positive slope graph and negative slope graph. Those negative slope graph are more spontaneous reactions, and those graph which are positive slope, they are non-spontaneous reaction. Now if you really look at the graph, you can see here there is a steep slope. So when you can see even the same here, this graph is going in this, and then suddenly it goes abruptly into the upper part. These actually represent the physical change in the graph, or this is what it is, the melting. So when there is sudden change or an abrupt change into the graph direction, it actually shows the stage change or physical stage change. For example, in case of zinc oxide at this particular temperature, zinc oxide melt and turn into the liquid stage. Same way here, magnesium oxide turns into the liquid state. So this is what we can understand. Here we have a special point A, that is what we are going to study in detail into the next point. But you just need to remember that we have two parallel graph for the formation of magnesium oxide and aluminum oxide. This magnesium oxide graph actually intersect into the aluminum oxide graph in a particular point A, and then above A the graph of magnesium oxide is above the graph of the aluminum oxide. So here the situation changes. That is what we are going to study in detail. This point A is representing the 1350 degree centigrade temperature. So this is what it is known as the Ellingham diagram. We are going to study this Ellingham diagram in detail, um, on one by one pages. Let us study about the Ellingham diagram in detail into the next video. Happy learning, my dear students.